All right, so my question here is, what does the Big Bang, a policeman measuring your speed, and weather forecasting have in common?
Radius wave.
Waves, radar, annoying, yeah? Light, speed of light. The answer is this, the Doppler
I said
effect.
that.
I didn't hear it. All right.
Oh, is that the subject of the whole PowerPoint?
So, these things all have the Doppler effect in common. Policemen use the Doppler effect to figure out how fast you're going. Doppler radar tells us how storm clouds are moving. And we know that the universe is expanding because of the Doppler effect. What is the wave formula? V equals F lambda. What determines the speed of a wave? The source, the medium, the amplitude, or the frequency? It's the medium, of course. The medium is the thing that determines the speed of a wave. Another way to say that, for any given medium, the speed of the wave does not change. For any given medium, the speed of a wave doesn't change. It doesn't matter what the source is doing, the speed of the wave through the medium doesn't change. So this gives us the Doppler effect, which is an apparent change in frequency of a wave source due to the motion of the source or the receiver. And this applies to what kind of wave?
All waves.
All of them, yes. Because a wave is a wave is a wave. This effect applies to all waves. All right, so where have you experienced the Doppler effect in your life? Here we go. You ready? Listen. All right, some observations. What did you notice? Did you happen to notice that the frequency of the horn changed? It went from a high frequency down to a lower frequency. Not only that, but it also got louder and then quieter. So if you were to graph out loudness versus distance, this is what the graph would look like. As the car was approaching you, the amplitude of the wave or the loudness got louder and louder and louder. When it was right at the same position as the camera, it was at its loudest. And then as it went away from you, the frequency receded. I'm sorry, not the frequency. The loudness receded, or it got quiet. But I'm going to ask you this question. How did the frequency change with the distance? So I want you to draw a graph of frequency versus distance. You can do it on the whiteboards. I will play the video again. So listen. All right, so what does it look like? It looks like this. Where as it's approaching, it's maintaining a high frequency. That moment that it's passing by, the frequency drops very quickly, but then it goes constant again. I will play it one more time. So you hear this in any kind of sound source that passes by, you hear this. Cars going by. A train whistle going by, an ambulance going by. As it's approaching you, it has a higher shifted frequency. And then when it passes by, the frequency drops. But the person inside the car always hears or ambulance or train or whatever, always hears a constant frequency. So what's going on here? What is causing this shift in frequency? Well, I have an animation here that shows a frequency, a sound being made by a jet plane. The sound waves are going out in all directions. So the sound waves are moving. What can we say about the velocity of the sound waves? The velocities of the sound waves is constant. For the source that's not moving, the wavelength, the distance from peak to peak, or area of high compression to the next area of high compression, is remaining constant. So people in all directions are going to hear the same frequency. But what if that source begins to move? Well, here they are moving along the same direction as this wavefront. So each source, or each sound wave, the wavelength gets compressed ever so slightly. So the wavelengths on this side are shorter, wavelengths on this side are bigger. What do we say about the velocity again? The velocity doesn't change, the velocity is constant. So if you have a constant velocity but the wavelength is shrunk, what happens to the frequency? V equals F lambda. If lambda gets smaller, frequency must get bigger. Or if the wavelength gets bigger, the frequency must get smaller. So as it approaches, the frequency shifted up. And then as it's receding or moving away from you, the frequency is shifted down. So this is how radar works. A radar sends out a known frequency. Well, somewhere that radar signal might bounce off of something like an airplane. But the bounce gets shifted because the airplane's moving. And that the difference in the frequencies between the sent out signal and the reflected signal tell the radar how fast that object is moving. This is how the police use it. Right? They have the device that does the calculations for them. But they send out a radar signal. It bounces off the car. And the radar signal, the frequency gets shifted because of the motion of the car. And the difference in those two frequencies will tell the velocity of the car. There's Justin Bieber getting pulled over. That's how he got busted.
Physics busted Justin Bieber, guys.
Doppler radar. The radar sends out a signal. The radar signal bounces off of raindrops, and that shifted frequency will tell how fast and how far away the storm is. What about the Big Bang Theory? Or not the TV show, but the Big Bang. How do we know that the Big Bang happened? When we look out at the universe, there's something that we notice, that galaxies that are close by average a spectrum somewhere in the middle. But the further away the galaxies get from us, like galaxies that are middle distance away from us, are shifted ever so slightly to the red. Bigger wavelengths. The galaxies that are really far away from us are shifted even more. Well, what does it mean if a frequency is shifted? It's in motion relative to us. So the furthest away galaxies are moving the fastest away from us, which is why they're the furthest away. This was figured out by Edwin Hubble about 100 years ago, well, 70 years ago. He realized that the further away a galaxy is, the more it's shifted towards the red end of the spectrum, which means it's moving away from us faster than galaxies that are closer.
Didn't they recently find twisted?
So there's a worksheet with pictures of these that I'd like you to go ahead and try working out some sample problems and then answer some conceptual problems on the Doppler effect. Thanks for listening. Goodbye.